Welcome back. I'm pleased to introduce Dr. Christine Galib, our moderator for the aerospace session. Christine is located at the Houston Ion, where she is the Senior Director of Programs and also Director of the Smart and Resilient Cities Business Accelerator. Christine, please tell us our audience about the Aerospace Hub at the Ion.
Sure. Thank you so much. And it's great to be here. It's great to be attending this great event. Pumps and Pipes obviously putting on a very collaborative event that encourages us to think through how different areas of innovation come together so that we don't solve the same problems in the same ways and thereby creating the same problems over and over and over again. So we're a huge fan of this work at the Ion. The Ion, of course, being the anchor of Houston's 16-acre innovation district. And so we've got a ton of great stuff going on over at the Ion. I'll just highlight a few main key points here. So I want to keep our focus on the Aerospace Innovation Hub for today, in keeping with the theme of today's session. The Aerospace Innovation Hub at the Ion serves minority business enterprises that are interested in either pivoting their tech from Earth to space or from space to Earth. So what do I mean by that? Basically, if you're a minority business enterprise working on any type of technology, product, or solution that could be used to help as we explore and activate space, we want you to come to the Aerospace Innovation Hub at the Ion. If you're interested in looking at NASA's current technology and seeing maybe they have something that you've been working on that you're interested in, and you would like to take their technology and apply it to applications here on Earth, terrestrial problems, that's another thing that we're working on as well. So we have this dual kind of tech transfer theme going on at the Aerospace Innovation Hub at the Ion. I'll welcome you at my booth a little later on today, but I wanted to underscore what the Hub will offer before I introduce today's speakers. The Hub will offer three main things: education and training, events that drive community engagement and promote a network of peers, as well as an accelerator program. So education and training, we think of things like upskilling, reskilling, data management, data analysis. Those types of programs will be offered through the Hub at the Ion. If you're interested in rapid prototyping, maybe you've never taken a CAD class before, maybe you want to brush up on your 3D printing skills. These are all types of education and training workshops that we will host at the Ion through the Hub. The second thing is community engagement events. So maybe you're working on some type of aerospace related challenge. Maybe that's telehealth, maybe that's telemedicine, maybe that's supply chain technology. Maybe that's something like a mining application that could be used to mine on the moon. You could come and build your own network or engage with a community of like-minded peers through our different community events at the Ion. And then the third kind of leg in our three-legged stool of the Hub is the Ion's Aerospace Innovation Accelerator, where if you're a minority business enterprise, maybe you're a startup or maybe you're a small business, and you're working on some type of aerospace-related technology, we would love for you to apply for our first cohort. We've actually got an event coming up on December 16th, and I'll put when I'm done talking, I'll put the link in the chat box so you can register there. But right now, I would love to turn it over to our speakers for today's speaking and panel session, and I'll introduce them before they start. We're very fortunate to have Martha Hess, Greg Meholic, and Julie Reese here today. So Martha leads the Aerospace Corporation's exploration portfolio. She works closely with executives and senior leaders across NASA and private industry on strategy development and change initiatives. She has led and managed large teams and budgets and regularly finds herself in roles where creativity and technical capabilities intersect. She constantly strives to make things happen for the people at all points in their career, education, or life path. Greg Greg has worked for the Aerospace Corporation for 19 years as a senior project leader specializing in launch systems, large rocket engines, future space vehicle concept development, and advanced propulsion technology. He currently leads several teams of technical experts on fission-based rocket engine development and the pursuit of fusion power and propulsion. Excuse me, I always get those two words mixed up, and they're not the same thing. He has published award-winning papers on a novel model of space-time that would permit faster than light travel and has been interviewed on many nationally broadcast radio and internet shows. Greg is the recent former chair of the Nuclear and Future Flight Propulsion Technical Committee of the American Institute of Aeronautics and Astronautics, of which he's been an active member since 1995. He was an adjunct educator for the Loyola Marymount University in the Seaver College of Engineering for the past 15 years. I'll turn it over to our speakers now.
Hey, thanks so much. We're really excited to meet today. In previous Pumps and Pipes, a lot of the focus has been put on NASA, and NASA represents about $20 billion of the space industry. And so at Aerospace, we work across the entire $342 billion space industry. And so there's a lot of space out there and a lot of connections that can be made with our Pumps and Pipes partners. And that's one thing that we always like to highlight at Pumps and Pipes from an aerospace perspective. One of the reasons we're really interested in talking to you about fusion today is we really feel like this technology is getting to a point where everyone needs to have a focus on it. And so I wanted to take this moment to introduce Greg Meholic, who will share with you the state of fusion and hopefully inspire you to start thinking about how fusion is going to impact your business and your lives in the future. So Greg, I'll hand it over to you. Thank you.
So hi, everybody. My name is Greg Meholic, and as I got the introduction from the prior two people that just want to say thank you for having me here. I am going to try to go to sharing this presentation, so hopefully everybody can see the charts up. What I'm going to talk with you about today is fusion, and I am going to tie this in some way back to human physiology and interaction as we go through the presentation, but just wanted to kind of give a background on all the hubbub that you might have been hearing about from things like Engadget and PopSci and Yahoo News and Popular Science and a variety of other organizations that have been talking about fusion and these stories that come up a little bit. But what is it, right? What is it that we can do with fusion? Well, fusion, first off, is a nuclear process that releases tremendous amounts of thermal energy, and it drives the sun. It's the process that drives all the stars that we see in different states, of course, because they're different sizes. But essentially what's going on in the sun is you're taking hydrogen atoms and you're fusing them together to make helium, not unlike the diagram that I have in the bottom of the screen there. But how does it work? Well, essentially the word fusion means to join, and this is exactly what's happening, is when you take two atoms, for example, in this one called deuterium and another one called helium-3, obviously very small, and you smash them together with extraordinary amounts of energy, you get a whole lot of energy that releases because you're breaking bonds inside of the atom. And all that energy comes out, as well as the formation of new particles. And so in the process, the holy grail of fusion, as you may have heard at some point, is that there's more energy that comes out of the process than goes into creating the process. And so that's sort of what is driving everybody towards this fusion technology, is that there's the possibility you could actually get more energy out than what you need to put into it. So there's a lot of technical challenges, as you can imagine, with this, but this is done. This is a natural occurrence. Like I said, it happens in the sun, it happens in the upper atmosphere, and we can actually do fusion in the labs here, in a variety of labs across the world, in a variety of different ways. There's more than just one way to do fusion, as I'll talk about just very briefly in the next slide. So the typical type of nuclear power that we've all grown up with is nuclear fission, right? Ever since the 40s and the Trinity site and obviously World War II, fission has become the most prolific use of nuclear power. And by fission, we take a radioactive material like uranium or plutonium, and it's emitting all kinds of stuff, mainly in the form of high energy neutrons. And neutrons are obviously subatomic particles, but they're heavy, they don't have any charge, and they move very fast. And what that means is that it can pass through, neutrons can pass through all sorts of things, unimpeded by the mass that they pass through. And in doing so, can go into things like DNA and go into tissue and start wrecking the cells at the tissue at the cellular level and the atomic level. So neutrons are kind of considered really not very healthy to be around, so to speak, unless you're using them in a controlled manner. But fission results is basically where you have high energy neutrons that are smashing into this thing called a target nucleus, which might be another uranium atom. More neutrons come off, more fission products come off, and each one of those fission products also produces neutrons. And so you have this cascade effect. So this is a naturally occurring phenomenon also. I mean, and natural radioactivity is based on this. And when you have these high energies and these small particles coming out, there's a way to use that to generate a lot of heat, obviously, when you start breaking bonds, which is what fission is, and you get the energy released that way. Fusion, on the other hand, as I mentioned before and how that works, it is supposedly be able to produce more energy than is required to sustain it. You can't just normally start, there's nothing you can pick out of the ground that is naturally fusing, right? You have to have two things that you have to force together to get that to work. But at the point where you have more energy being produced from breaking those bonds and fusing those two things together than it takes to slam them together, that's when you get this break-even point. That is sort of the holy grail in the energy world. In that, if you get more energy out than you put in, that's huge, right? Right now, we're pretty close to that, but obviously there's a lot of other technical things that come in that are involved in order how to sustain this sort of thing. Fusion offers also less radiation production than fission. Because you have high energy other subatomic particles coming off, those also help to fuse other atoms and give those a kick. Not unlike when you hit if you're playing a game of pool and you hit the rack with the white cue ball and everything sort of scatters. That's sort of the kind of the atomic motions that go on inside of these processes. So it does offer less radiation, depending on what you fuse together and how you fuse it. And the key to why fusion is so much more attractive than fission is because of the ultra high temperatures that are produced in a fission reaction. Fusion. I keep saying fission. In a fission reaction, typically like what goes on in nuclear power plants and it goes on in the bellies of naval vessels and things like that, you get temperatures in the several thousands of degrees, 2 to 3 or 4,000, maybe even 6,000. You can get really, really hot, but obviously it takes a lot of, special metallurgy and so forth to keep those things cool. However, when you talk fusion, you're talking tens of millions of degrees, surface of the sun, internal to the sun type temperatures. So orders of magnitude more than what you can get out of nuclear fission. And when you have that type of thermal energy to deal with, it cannot take the form of metals or ores because those will just melt. They take the form of what's called a plasma. And in a plasma, in the engineering world that we deal with, plasma is a gas that's made up of charged particles, unlike what plasma is dealt with in the medical industry, which is one of the contents of blood. This is very different, right? So when you take this high, extremely high temperature charged with electricity or different types of charges, this gas that is millions of degrees, it offers a lot of opportunity to do work with it. Whether or not you want to push a spaceship or if you want to turn a generator. But the fact is you have these ridiculously high temperatures that need to be contained, need to be managed and monitored, but that you can get out of fusion compared to fission or compared to any other chemical process that we have. So moving on to the next chart, here's just some pictures of what's going on with fusion power and fusion propulsion. So at the top here, I just have 3 slides of fusion power. This is at one of the labs, I think in France. And you can see the gentleman inside of one of these fusion reactors. And in the middle here is what the fusion plasma looks like. It's like this glowing blue halo. And that's where the actual fusion is going on. And on the upper right is sort of an artist's deception of how you can take this fusion reactor called a tokamak in this particular form, and then use it to generate heat and output power to the national grid and so forth. So this is one way to use fusion, the fusion thermal system for power. Looking at propulsion, a few folks many years ago had said, well, if you can do fusion power, why not just cut this thing in half and stretch it into a line? And now you can eject these fusion products along with other propellants out the back and make sort of a rocket engine out of this. And that's exactly what this does. So, I have some pictures of with those similar concepts on the bottom. So why is fusion propulsion so much more attractive than a fission propulsion system or even a chemical rocket? Well, the fusion propulsion system concepts right now are not just 1 or 2 or 3 times more efficient than the chemical systems we have today, but they're like 1,000 times more efficient, all right? Or maybe not quite 1,000, but definitely 100 times more efficient. And, you can get extraordinarily good fuel economy with these types of systems. The thrust is still a little bit low because you're dealing with these very, very, very light particles, but there's ways to build your spacecraft around that. But let's go to the next chart and talk a little bit about the spacecraft, how you would use these fusion engines compared to a fission spacecraft. So the fission-powered spacecraft being envisioned right now for the future at the top, this is one of NASA's older models, but this is what they are considering going to Mars in, is something that's based on nuclear fission, where you take uranium, you heat up a hydrogen propellant, you send it out the back of a rocket engine, and you push the vehicle towards Mars in about 160 to 180 days, which isn't all that bad, considering chemical rockets like the typical space shuttle main engine or something would take twice as long, okay? But the fuel economy of a fission system is actually pretty good. You can generate electrical energy and propulsion at the same time, but you need cryogenic liquid hydrogen fuel, which costs a lot of energy to keep cold. And you have limited fission processes available to you. Basically, it's uranium, it fissions and causes heat. And there's just 1 or 2 other ways you can capitalize on that. But nonetheless, this particular concept has been looked at for decades. It's been studied. Looking at a fusion spacecraft concept, however, brings about some additional advantages and also some technical challenges. Number one is there's less radiation to the crew compared to a fission system where there has to be special shielding and so forth. It can also produce energy and propulsive power at the same time. You have these ultra high efficiencies engines, so you don't need as much fusion fuels as you need in a fission concept. And there's multiple fusion methods. There's something called IEC and MCF and ICF and a variety of others. There are ways that we've actually demonstrated on being able to do fusion in the lab and sustain it in some way. And then there's pulsed versus steady state. But some of the fuels that you need to actually do this are extremely rare. And Martha had mentioned about mining on the moon. That might be one way to get one of these fusion fuels that actually has a lot of advantages to it, called helium-3. It seems to be in abundance on the moon. So how do we go there and get that, where we don't really have any of it down here on Earth that we can work with? But what's important from a physiological perspective is that these fusion-propelled spacecraft could offer shorter mission times. And I'm not talking shorter by a day or two compared to the fission system. It might be you only get 60 to 90 days to go to Mars instead of 160 days or 190 days. And so what that means to the astronauts that are on board these fusion spacecraft means that they are less exposed to zero gravity. And there's been countless studies on how zero gravity has both positive and adverse effects to the human body. It also limits their radiation exposure to cosmic background radiation and radiation from different magnetic fields and a variety of other things that are out there. So it cuts down all of that physiological exposure by having these shorter mission times, thanks in 100% part to this fusion-based propulsion system. So that's kind of why, on the propulsion aspect in the advanced concepts world, we are looking at this pretty heavily and seeing what kinds of subsystems would be involved and how to make one of these things work, and what sort of technical considerations have to be looked at for fusion, as well as fission. That's also very active. So challenges with fusion being addressed, obviously fuel production and storage. How do we get this helium-3? How do we get 25,000 gallons of deuterium and keep it in a cold state for months on end in space? how do we provide the energy to start the fusion reaction, right? Because I mentioned it takes energy to start this. It's not a naturally occurring, thing. So we might need, hundreds of thousands of watts in space or megawatts in space, and that is far in the future right now. How do we contain this, 10 million degree plasma from burning up the rest of the engine? How do we extract power and convert that to electricity to run the environmental systems for the spacecraft, any kind of instrumentation or whatnot, as well as the engine itself? And how do we get rid of all the waste heat? That's a big, big issue, because no matter how good of an engine you have, you're going to have a heat that's left over that you have to get rid of. There's no perfectly efficient thermodynamic cycle, of which fusion still is, that will be able to use 100% of the heat that's generated in the cycle. Same with your car engine, same with the jet engine, same with the most efficient rocket engines, or even these engines. Somewhere you got to get rid of the heat. And fusion engines and fission engines both have an extraordinary amount of heat that you just can't use any longer. So that's a big technology challenge as well. But to the credit of all these are all still being very actively looked at by a number of different startups, number of different companies, all which have extremely innovative and great ideas that when they come to aerospace and we hear about them, we want to try to make sure that we know about them and that we might be able to help them in some way if we see a benefit to our customers and to them to further the technology along for not just our customers, but the good of others. So with that, I just wanted to say thank you for your attention. And, just to point out here, there is significant progress being made. So thank you once again for having me. It's been a pleasure.
Yeah, thanks so much, Greg. That was a great talk. Really appreciate it. So thank you so much for this time.